pH homeostasis, or the regulation of the extracellular proton concentration, is one of the most remarkable regulatory processes in the body. It is often underappreciated how tightly controlled the free proton concentration is due to the use of a pH scale, which is the inverse log of the proton concentration. For comparison, recall that the normal extracellular sodium concentration is approximately 140 millimolar, plus or minus, say, 10 millimolar or so, within a normal physiological range. By contrast, the physiological proton concentration has a pH of approximately 7.4. Because this is an inverse log of the proton concentration, this equates to approximately a 0.00004 millimolar concentration, or a 40 nanomolar concentration of the free protons, give or take 10 to 20 nanomoles or so. So this concentration is approximately 3.5 million times smaller than the sodium concentration. But even though it's small, it's extremely important. Small deviations from this concentration are deleterious to the function of a variety of processes and life itself. To put this in perspective, if the sodium concentration is the length of the football field, plus or minus the end zones for its normal physiological range, then the free proton concentration is the size of a few red blood cells end on end, give or take a red blood cell or so. How is the extracellular proton concentration regulated? Regulation is largely accomplished by two main organ systems, the respiratory system and the kidneys. First, let's talk about the respiratory system. The respiratory system has a rapid influence on pH by modulating the partial pressure of carbon dioxide, influencing the dissolved carbon dioxide concentration. Recall that carbon dioxide reacts with water to produce carbonic acid, which dissociates to a bicarbonate and a proton at physiological pHs. This reaction is in equilibrium within the blood, such that changes in PCO2 can cause changes in the free proton concentration. An increase in the PCO2 causes an increase in the rate of the production of protons, resulting in a reduced pH. Conversely, a decreased PCO2 causes a reduction in the rate of proton concentration and an increased pH. Another way of thinking about this relationship is in terms of the Henderson-Hasselbalch equation. Without going into all the details of this equation, the one feature I'd want to emphasize here is the relationship between the ratio of the bicarbonate concentration and the carbon dioxide concentration, determined by the partial pressure of carbon dioxide and the solubility of carbon dioxide for water, and the pH. So the pH is a function of this ratio. Therefore, changes in this ratio can produce changes in the pH. Based on this ratio, it should be clear that an increase in the carbon dioxide concentration results in a reduction in the pH, whereas a decrease in the carbon dioxide concentration results in an increase in pH. The other important system for the regulation of extracellular pH are the kidneys. The kidneys exert long-term control of extracellular pH. This is accomplished by a variety of renal processes, but probably the three most important processes are the reabsorption of filtered bicarbonate, or not, and I'll come back to that in a moment, the secretion of protons, influencing the net acid excretion, and then the production of what's called new bicarbonate. Note the new in quotes. First, let's discuss the reabsorption of filtered bicarbonate. So bicarbonate is the second most abundant anion in the extracellular fluid, including the blood plasma. And nearly all of the bicarbonate that's filtered within the glomerulus is reabsorbed in the proximal tubule, put back into circulation. I don't want to go into the mechanisms of bicarbonate reabsorption here. It is a complex process. One important feature of this reabsorption process is that the kidneys have a finite capacity to reabsorb bicarbonate within the proximal tubule. In fact, when bicarbonate concentrations are normal, somewhere in the range of 24 milliequivalents per liter, this concentration of bicarbonate approaches the transport maximum for bicarbonate, meaning that if the bicarbonate concentration increases above and beyond its normal concentration, the transport mechanisms that reabsorb this bicarbonate become saturated, and that excess bicarbonate that was filtered does not become reabsorbed and therefore ultimately becomes excreted into the urine, because the other nephron segments lack the ability to reabsorb an appreciable amount of bicarbonate. So basically, under normal conditions, bicarbonate is filtered within the glomerulus, and nearly all of it is reabsorbed in the proximal tubule. If bicarbonate concentrations increase, and this is something that we'll see that occurs underlying metabolic alkalosis, then this excess bicarbonate does not get reabsorbed and ultimately becomes excreted. The second process, the secretion of protons modulating net acid excretion. The area of the nephron that's mostly responsible for modulating net acid excretion, that is, for controlling the rate at which we're eliminating protons from our body, is in the late distal tubule cortical collecting duct area. Again, without going into all the transport details here, the main source of these protons is carbon dioxide reacting with water to produce the bicarbonate in the free proton. The protons produced by this reaction are secreted out into the tubular lumen, where they can ultimately become excreted. So what happened to the bicarbonate that was produced in this process? This represents the production of new bicarbonate, or the third renal process for modulation of extracellular pH. So the bicarbonate that was produced by this reaction between CO2 and water is retained by the body. That is, it is transported back across the basolateral membrane and moves back into circulation. Recall the Henderson-Hasselbalch equation, where the pH is a function of the ratio between the bicarbonate and the carbon dioxide concentration. Note that this secretion of protons and production of new bicarbonate produces a net increase in the bicarbonate concentration and a net decrease in the carbon dioxide concentration. This will obviously lead to an increase in the pH. So one important feature about this, we call this new bicarbonate because this process causes an increase in the bicarbonate concentration. This is different than the reabsorption of filtered bicarbonate, which simply preserves the bicarbonate concentration. That is, reabsorption of the filtered bicarbonate doesn't cause the extracellular bicarbonate concentration to increase, it just prevents it from decreasing, at least under normal circumstances. So we have these two physiological systems that are important for the regulation of extracellular pH. We have the respiratory system, which can exert rapid changes in the pH by modulation of the partial pressure of carbon dioxide. The renal system has a slower, longer-term effect on pH by modulating the net acid excretion and by the production of new bicarbonate. Because we have these two different mechanisms for the influence on the extracellular pH, acid-base disorders are often categorized by whether their cause is respiratory in nature, as in some impairment to respiratory function, or if it's metabolic in nature, usually due to either impairments to kidney function, overproduction, or excessive loss of either protons or bicarbonate from the body. Additionally, challenges or deficiencies to one of these systems can be partially compensated for by a concerted response from the other system. So real quick, we have four basic categories of acid-base disturbances. We have respiratory acidosis, respiratory alkalosis, metabolic acidosis, and metabolic alkalosis. So what are some quick examples of these different conditions? Respiratory acidosis is characterized by an increase in arterial PCO2. This can be due to either an impairment to ventilation, say during a restrictive pulmonary disease such as fibrotic lung disease, or it can also be due to impairments in gas exchange, such as the case with conditions like pneumonia and emphysema. Respiratory alkalosis is a decreased arterial partial pressure of carbon dioxide. This is not as common. This usually involves hyperventilation. The hyperventilation can be either psychogenic or can be caused by exposure to high altitude environments. Metabolic acidosis, there's a variety of causes that fall under this category of pH disturbance. The examples are renal tubular acidosis. This can be impairments in bicarbonate reabsorption or proton secretion, so the kidneys are unable to modulate extracellular pH appropriately. Diarrhea, resulting in excess excretion of sodium bicarbonate. That loss of bicarbonate, which is a base, causes the extracellular fluid to become more acidic. Also, ethylene glycol toxicity is the main active ingredient, antifreeze. It's sweet tasting. It can be ingested by an unsuspecting child or animal. It gets produced into oxalic acid within the liver, and it promotes acidosis. So there's excess production of protons in the body, resulting in metabolic acidosis. And examples of metabolic alkalosis are the vomiting of gastric contents, resulting in net proton loss from the extracellular fluid. Ultimately, this can make the extracellular environment more alkalinic. Overdosing on antacids, where the main active ingredient of certain types of antacids are sodium bicarbonate or sodium or calcium carbonate. This increases the alkalinity of the extracellular fluid, resulting in alkalosis. And administration of diuretics as well. Most diuretics, not counting the carbonic anhydrase inhibitors, can produce alkalosis. They do this by inhibiting sodium reabsorption somewhere in the nephron. This increases the sodium delivery to the distal nephron segments, resulting in increased proton secretion due to the presence of these sodium proton exchangers. So you get this excessive secretion of protons, which then ultimately become excreted, and this can promote alkalosis. How does one go about distinguishing between these acid-based disturbances, what the causes are, and then ultimately trying to determine whether there's some sort of compensation that is occurring by the unaffected system? This acid-based disorder analysis does a good job of at least providing the rationale into how one approaches these types of situations. And we start with an arterial blood sample. And with that sample, the first thing we ask is, well, what's the pH? Because a normal pH of 7.4 is the pH less than that, or is the pH greater than that? If the pH is less than 7.4, this would indicate acidosis. So then the question is, well, is this metabolic acidosis or respiratory acidosis? There's different ways of trying to distinguish or differentiate between these two causes. I feel like the most intuitive is to either rule in or rule out respiratory acidosis first. Just because the relationship between the partial pressure of carbon dioxide and the blood pH is relatively straightforward. Because carbon dioxide is an acid, if the amount of carbon dioxide is higher than normal, that would indicate respiratory acidosis. So that's the way I usually approach this. So let's say, again, pH less than 7.4, so we say acidosis. The question I ask then is it respiratory acidosis? So we look at the PCO2. If the PCO2 is greater than 40 millimeters of mercury, significantly greater than 40 millimeters of mercury, that would indicate respiratory acidosis. Then the next question would be, is there renal compensation? Let's think of how the kidneys would try to compensate for this respiratory acidosis. So first of all, the kidneys could increase the rate of proton secretion, thereby increasing the net acid excretion. So that's one. But also, and in the process of that, the kidneys would be increasing the rate of new bicarbonate production. So because of this, we would expect to see the bicarbonate concentration climb, be in excess of the 24 milliequivalents per liter or so, which is the normal range. So if we see that the bicarbonate concentration is significantly greater than the 24 milliequivalents per liter, then we would say that there is evidence of renal compensation. So from the top, if the PCO2 is greater than 40 and the bicarbonate concentration was greater than 24, we would say respiratory acidosis with renal compensation. Okay, now let's go back to acidosis and let's assume that it's not respiratory. We look at the respiratory system, or we look at the partial pressure of CO2. It's not greater than the normal of 40 millimeters of mercury. Because of this, we could rule out the respiratory system and we could just say metabolic acidosis. Note that this would be associated with a decrease in the bicarbonate concentration, because if we are acidic, those free protons are going to react with the normal bicarbonate that's floating around in circulation, thereby reducing the bicarbonate concentration. Regardless, we say metabolic acidosis because we ruled out the respiratory system. So then the next question is, do we see evidence of respiratory compensation? What would that compensation look like? Well, the respiratory system would increase alveolar ventilation. Remember, the decrease in pH would stimulate the activation of the peripheral chemoreceptors, causing an increase in alveolar ventilation, dropping the partial pressure for carbon dioxide, less than 40 millimeters of mercury. So if we see that, then that would indicate metabolic acidosis with respiratory compensation. Okay, back to the pH. Now let's assume that the pH is greater than 7.4. So now we're alkalinic. So we say alkalosis. And again, the same logic, the first thing I would do is I'd either rule in or rule out the respiratory system. For the respiratory system to be the cause of the alkalosis, we would expect the partial pressure for carbon dioxide to be less than 40. And so if that's what we see, a PCO2 of less than 40 due to hyperventilation, then we would say respiratory alkalosis. Next, is there evidence that the kidneys are compensating for this respiratory alkalosis? How would the kidneys compensate for this? It's probably tempting to say that they would do this by decreasing the reabsorption of the filtered bicarbonate, but this is not a significant mechanism for the correction of respiratory alkalosis. That is because as long as the bicarbonate concentration is normal or less, the reabsorption of that filtered bicarbonate is nearly maximal. So how are the kidneys going to then respond to this respiratory alkalosis? They can decrease the rate of new bicarbonate production. So under normal conditions, you're producing some normal amount of new bicarbonate. In the case of respiratory acidosis, the kidneys could increase the rate of that production to compensate for that respiratory disturbance. In the case of respiratory alkalosis, it goes the other way. The kidneys can decrease the rate of new bicarbonate production, resulting in a net reduction of bicarbonate. So taken from the top, if we are alkalinic and the PCO2 is less than 40 millimeters of mercury, we say respiratory alkalosis. If the bicarbonate concentration is less than 24, we would say respiratory alkalosis with renal compensation. And back to the top again, if we rule out the respiratory system, that is, the PCO2 is not less than 40, we could simply conclude that this is metabolic alkalosis. Note that metabolic alkalosis is associated with an increase in the bicarbonate concentration. Often this is because of the alkalosis, like the overproduction or ingestion of that bicarbonate. So now the question is the respiratory system compensating? How does the respiratory system compensate? It compensates by decreasing ventilation. Again, this is stimulated by the peripheral chemoreceptors. They detect the increased pH of the blood. This causes a decrease in ventilation, which increases the partial pressure of carbon dioxide. So if we see that the partial pressure for carbon dioxide is elevated, then we would conclude metabolic alkalosis with respiratory compensation. So this disorder analysis is useful for understanding the logic of how acid-base disturbances are characterized. There are a number of shortcomings with it. For instance, not all acid-base disturbances fit so neatly into these binary yes-no types of circumstances, like you can have mixed acid-base disturbances. Also, like in the case of metabolic alkalosis, we say respiratory compensation occurs when the PCO2 is greater than 40 millimeters of mercury. How much greater than 40 millimeters of mercury do you expect it to be? 45, 50, 55? This gets lost in this simple disorder analysis. A more sophisticated way, and I think a more useful way of approaching these relationships is with the Davenport diagram. If you're interested in understanding more about acid-base disturbances, you should definitely check out how these processes are represented within a Davenport diagram.